Alright guys, so now this lesson what we're going to do is introduction to chapter 6, and which is talking about normal distributions. So before on chapter 5, prior to the break, we talked about discrete distributions such as the binomial distribution. Now we're going to look at continuous distributions, and one of which is the normal distribution. This is actually the special one that we'll actually focus on because there's so many applications to it in probability and statistics. So we're going to look at the properties of the normal distribution, and then we're going to look at how do we identify distributions, whether as symmetric or skewed, which we kind of talked about before, but we're going to kind of quickly review that. And then we're going to focus on finding the area under the standard normal curve given various z values. This will make more sense later on. Alright, so now let's get started. So let's recall the definition of a random variable. So a random variable is a variable that can occur either is a variable that can take on different values, and it's based off of chance. So random variables can take on whole values, whole numbers, or decimal numbers, right? So they can either be discrete or they can be continuous. Let me this out of the way. So they can be discrete or continuous. Discrete variables, remember, these are whole numbers. They can take on any they cannot assume all values between any two given numbers. So like between 1 and 2, or like between 1 and 4, for instance. You can take on 1, you can take on 2, you can take on 3, you can take on 4, but you can't take on numbers like 1.5, 1.2. You can't take on decimal numbers. So it's usually a whole number, and it's usually the result of something that is counted. So it's usually countable, like the number of hot dogs, that were cooked in a barbecue, for example. Different examples like that involve something that is counting. Continuous variables, on the other hand, generally are stuff that are a result of something that is measured, and it can take on multiple values. So it tends to be a decimal number. So, for example, height, body temperature, and cholesterol level. Those are all things that are measured and can be written as decimals. So like 98.7 degrees Fahrenheit is the typical body temperature, human body temperature, for instance, etc. Many continuous variables have distributions that are bell-shaped, and these are called approximately normally distributed variables. A normal distribution curve has this bell shape, and we have a couple different names for it. We usually call it a bell curve. And so another name for it is a Gaussian distribution. This is named after a mathematician whose last name is Gauss. So, and that's where it comes from. So the graphing equation. So this is the equation of the normal distribution. You don't have to know that equation. You just have to know that it depends on a couple things here. So it's dependent on sigma, and it's dependent on mu. And those are the values those are the two parameters that change the shape. So we know how the bell curve looks like. This is the shape of the bell curve. But the shape and position of the bell curve, or the normal curve, depends on these two parameters, which is the mean. The mu is the population mean, and sigma is the population standard deviation. So these two parameters are what change characteristics of the curve. So the mean changes the position of the curve. So let's say this mean was 5. If it were 6, then it would change the bell curve so it looks like that. So the mean changes the position. the standard deviation changes the shape. So for instance, if the standard deviation were a big number, then it would make the curve more spread out. Standard deviation is a measure of spread, remember? So when it's bigger, then that means the curve is more spread out, which means that the curve is wider. If the standard deviation is smaller, which means it's not as spread out, then the curve is going to be skinnier because there's less spread. There's more clumping and there's less spread. So the standard deviation changes the shape. Greater standard deviation means so a greater standard deviation means that you're going to have a less spread, so a more spread out curve. So more spread, which means that you're going to have, so if this were your original and you have a greater standard deviation, then you're going to have a flatter curve. Okay, so a flatter curve. All right, this is an example of how it looks like. So if you were to change the mu is 0 here. If you were to change it to 2, then it changes the position. If you were to change the sigma from 1, which is the brown, to 2, then it becomes more spread out and flatter, more like a pancake when as you get to bigger values. All right, so what are some of the properties of the bell curve? So a couple of properties that we want to mention. So we know that it's bell-shaped. All right, that's why it's known as a bell curve. We know that the mean, if you look at the curve, the mean, median, and mode are actually all located in the middle. So they're all equal to each other, and they're actually all located at the center of the bell curve. The curve is symmetric, which we can tell from the graph. It's symmetric about the mean. The curve actually is continuous. It goes on forever, and it doesn't have any gaps or anything like that. So it's continuous. The curve actually never touches the x-axis. So if you were to look at the graph, it's never quite touching that x-axis. However, even though it never touches the x-axis, one of the interesting properties is that the total area under the curve is equal to 1 or 100%. There should be a percentage there. A normal distribution curve is unimodal. So unimodal means it only has one mode. And the mode is in the middle. So the area under the part of the normal curve that lies within one standard deviation of the mean is approximately 68%. If you're within 2 standard deviations, this increases to 95%. And if you're within 3 standard deviations, then this increases to 99.7%. And what that's saying is that, and that's known as the empirical rule. That's a special rule, has a special name, known as the empirical rule. All right, so this is actually pictured below. So like the mean is in the middle, which is mu, right? If you were to go 1 standard deviation on each side, then you would have an area under the curve that is equivalent to 68%. 34 plus 34, so approximately 68%. If you start in the middle and you were to go 2 spaces on each side, so 2 standard deviations on each side, then you're going to cover about 95% of the curve. So that would be the area of everything here between those 2 marks, here and here. If you were to start in the middle, go 3 spaces on each side, 3 standard deviations, then that would cover almost 100% of the curve, 99.7%. And that's called the empirical rule. We're going to use that more in the next section or two. As we can see, the normal curve is symmetric. When the majority of the data falls to the right or left, then we call that skewed. When most of the data fall to the right of the mean, which means it looks like this, most of the data fall to the right, we call that negatively skewed or left skewed. When most of the data fall to the left, like that, then it's called right skewed. So it's said to be positively or right skewed. All right, and below is a picture of how that looks like. So this is going to be negatively skewed, positively skewed, and then normal. All right, so the standard normal distribution is a normal distribution with a mean. So this is different than a normal distribution. So it's still going to have the same shape as a normal distribution, but we call it a standard normal distribution. The reason why we call it standard is because it can be converted from any normal distribution into this standard normal distribution, where it always has a mean of 0 and it always has a standard deviation of 1. So like if you were to measure something like weight or height, for instance, that may follow the shape of a bell curve, but that doesn't mean that the mean height of someone will be 0 or the standard deviation will be 1. So in general, if you have a measurement such as height, let's say the average measurement of a male is 6 feet. And you're measuring different males or different people, then in this instance you're going to have something that resembles a bell curve, but you want to transform this 6 feet in the middle, you want to transform it to a standard curve, and that's called standardization. And so in order to transform it to 0, you got to transform it to a standard normal curve, and in order to do that, there's a formula for that, which we'll talk about right here. It's actually this formula. So in practical applications, just like in this example, it's necessary to convert it to a standard normal curve in order to use a table of values under the curve. We'll talk about how that table of values looks like in a second. So to transform it, then you would need the formula for the z-score. This is known as the z-score or the standard score. So this z-score or standard score helps us find the area under the normal curve, because once we get that z-score for any value, remember we can have any kind of measurement here, and we could still find the z-score if we transform it. Once we get that z-score, we can find the area underneath the curve, because sometimes we'll get a z-value that's not -1. Sometimes we'll get something in the middle, and we want to figure out what that area is, because that area actually symbolizes something important that we'll need in future sections. So how do we find that area? So in this section, I will make a note that we're not going to use this formula in this section. We're going to use this formula in the next section. And in this section, we're just considering if they give us a z-score, how do we find that area? So let's find that area. Let's figure out how to find that area. So step 1, we want to draw the normal curve and then shade the area that we want. And then to find the actual area, we follow the procedure below. So if we're given a z-value and we want the area to the left, then we need to look up the z-value in the table and then use the area that the table gives us. If we are, for example, looking to the right of a z-value, then we need to look up the z-value from the table and then subtract the area from 1. If we have 2 z-values and we want to find the area between those 2 z-values, we'll need to look up both z-values on the table and then subtract the areas from each other. So what is the standard normal curve? What is this table? How do we get this table? So this is actually the table that you were provided with. So it's a table in Appendix E on the book, on the ebook. So this is how the table looks like. All right, so this is the standard normal curve table. You have it for negative z-values and you have it for positive z-values, and these are the areas. So these are your z-values, and then in the middle are your areas. Okay, so here they want us to find the area under the standard normal curve to the left of z equals 2.09. So we're going to go ahead and quickly draw that. So we have this guy. Remember at the center you have 0, 1, 2, and we're looking for 2.09. So, you know, around here we have z equals 2.09, and we want the area to the left of that guy. So we need a shade to the left. All right, how do we find that area? Well, we're going to use the method given above. So let's see here. So we're going to go here. It says to the left of any z-value. You're going to look up the z-value and then use the area. Okay, so we're going to look up the z-value. We need it for 2.09. So we're going to go at 2.0. So this is 2.0 and then 9 right here. So 2.09 looks like it's 0.9817 right there. So that is our area. So area equals 0.9817. Let's go do the next example. So in this example, we want to find the area to the right of that z-value. So we're going to quickly draw it. So negative 1.14. We want the area to the right. So in order to find the area to the right, you're going to look up, at this guy. You're going to look up the z-value and subtract 1 from it. All right, so we're going to look at the z-value and subtract 1 from it. So we have negative 1.14. So we need the negative numbers. So negative 1.14. So we got, oops, wrong one. So negative 1.1, negative 1.14. So that's 0.1271. 0.1271. And then we got to subtract 1 from it, right? So we got to do 1 minus 0.1271. And that will give us 0.8729, if I did that math correctly. All right, so now let's do the area between those two z-scores. So we got 0, 1, 2, negative 1, negative 2. So we got negative 1.35 and 1.62. So the area between those two. So we need to find the two areas and subtract them. That's what it says here. Look at both z-values and subtract the corresponding areas. So negative 1.35 and 1.62. So negative 1.35. 0.0885. And then we got 1.62. 0.9474. All right, so we always subtract the bigger one and then the smaller. So bigger minus smaller. So we go ahead and subtract those. Let's figure out what that area is on the calculator. So 0.9474 minus 0.8589. All right, and that will be the area between those two. All right, so why do we need the area? So the area actually has an interesting property to it. And the property is that the area actually represents probability. So remember last couple of chapters we've been talking about probability, and this chapter is no different. So this chapter actually we're going to be doing probability problems, but we're going to be using the normal curve to answer those problems. So that's where the area comes into play, and it's actually really useful. So to find the probability, you simply find the area. So if they're asking for probability for a normal curve, you're just going to be doing the area. So finding the area between two z-scores. So basically you have your z is equal to 0, 1, 2, 3, and 2.53. So you're finding the area between those two. So you're looking at the probability of z being less than 2.53. This is the value that the table gives you. And then you're going to subtract that from the value for 0. Remember that the table gives you, if you were to look at the table actually gives you the area to the left. You see that picture there? This picture right here, it actually gives you the area to the left, which means where z is less than a number. So that's why I use z is less than. So I look up the value for 2.53 and the value for 0. And this is how I write this in notation. So you can practice. This is how you go about writing it. So the probability that z is less than 2.53. So then we're going to look at 2.53, 2.5, 0, 1, 2, 3. This is 2.53, right? Yep, 2.53, 0.9943, and then for z is 0 is 0.5. So 0.9943 minus 0.5. 0.9943 minus 0.5. And that's going to give me 0.4943. Now they want the probability that z is greater than 1.98. So remember, if we want to the right, this means to the right. And this is between two values. This means to the right. So z is greater than 1.98. So 0, 1, 2. So this is 1.98. We want to the right. That means we need to subtract the area. We need to get the area from the table and subtract it from 1. So get the area from the table. If you look at here, look up to the right, look up the z value, subtract the area. So in order to do this, we're going to be doing 1 minus the probability for the table, which the table gives us the left side. So we need to look at 1.98 on the table and subtract, and then we're done. 1.98, 0.9761. That'll give us 0.0239. All right, and that's all there is to it.